So let me start with thanking the organizers for the invitation. Our adventure with NeaSpec and nano-IR spectroscopy, microscopy started a few years ago, but telling the truth, the first material we brought appeared to be so nice that we had to invest then a few years to really realize to invest in studies to reach the level that we are right now. So I hope that I'm going to present almost complete story right now. So thanks to my previous speakers, I will not reintroduce polymer brushes, just to mention that this is a very idealized picture. So depending on the grafting density, we can either deal with really stretched polymer chains, but if the grafting density is too low, we rather deal with mushroom-like or pancake-like conformations. So we aim at this extended brush conformation. So basically you can vary the architecture of the polymer brushes. So we worked with a number of this type of architectures, but today I'm going to focus on so-called mixed polymer brushes or mixed binary polymer brushes. So when you have two types of polymers attached to a surface. And they are going to be also conjugated polymers. So just a brief introduction that conjugated polymers exhibit either not yet super, but I'm aiming at super, semi-conductive or just conductive properties, and they find applications in photovoltaics and organic LEDs or future nano or molecular electronics. So this is a very hot topic also for example, photovoltaic applications. And apparently in organic or polymer photovoltaic cells, you can find polymers both in the active layers when you have this thiophene-based polymers, but also in some layers like this PEDOT-PSS here or in different configurations, but which are known to be whole transporting layers. So those types of, or various types of conjugated polymers are really demanding, are really used in photovoltaic cells. And especially if you consider, let's say, the ultimate configuration. Okay, currently we are mostly dealing with so-called bulk heterojunction systems. But if we would like to reach really high efficiency, this is considered to be a kind of ultimate architecture with the nanorods or even molecular chains forming such a ordered structure. So this is like ordered heterojunction. So let me just focus on one example, this PEDOT-PSS, which is kind of thiophene-based polymer with polyelectrolytes that serve as dopants. Yeah. So you can buy, commercially such a mixture. You can spin coat them, this layer, and what you deal with is usually simply disordered system. Yeah. So and basically, if you consider conductivity, there is much higher conductivity in plane than out of plane, which is kind of not desired, I would say, for the construction of solar cells. So we would like to aim, with the help of the polymer brushes, to actually get ordered systems with a highly anisotropic conductivity, preferentially in the direction perpendicular to the grafting surface. As I said, classical films suffer from the disorder. There is usually isotropic electron flow, so we would like to address this issue. I will not investigate this. So what we came up with the idea of producing conductive or conjugated, generally speaking, brushes, just briefly, because this is not a synthetic conference. It's just to show that there are hardly any methods to really grow them in a controlled manner. So we introduced the bifunctional monomers so we can grow kind of ladder-like systems. Yeah? So we grow first the polymers using conventional polymerizations, pre-order the groups, and then polymerize the second chain, resulting in formation of conjugated chains. Of course, this is not the ideal system, so we also deal with not only intramolecular conjugation, but also intermolecular conjugation, but still, sorry, this is, okay, sorry, this is the next slide, but anyway. So there are a number of steps to reach that level. This is already like doped conjugated brushes. But these are some examples of the monomers that we already used and actually successfully obtained either semiconductive or conductive brushes after certain doping. And as I said, we don't necessarily deal or exclusively deal with this ladder like systems, but we also have to deal with like bridging, intermolecular cross-linking. Anyway, mixed brushes. So how to preserve the extended conformation of the chains, and having this mixture of polymers, similarly to this P.PSS, when you have conjugated brushes and the polyelectrolyte brushes. That's what we did. Also very briefly, because this is not the topic of, so I'm going to go to the spectroscopic and microscopic analysis. So basically we grow one type of the brushes, then cleaved some of them in a controlled manner, and let's say put some seeds, and grew the other types of brushes. So basically we have kind of polythiophene based brushes, and between them we have polysodium sulfonate, polysodium styrene sulfonate brushes, so polyelectrolyte brushes. So we really hope to get kind of molecular level of mixing. Because for that, we could, I mean, for such a configuration, we could reach really desired properties. So what we realized that depending on the contribution of those types of polymer chains, we can vary the features. So we can observe certain kind of phase separation that we actually wanted to address, and this is the very topic of this talk. So we didn't know, of course, from the regular AFM images, you don't know what is where, if they are holes or they are just depression, similar to the previous speaker. We need to have chemical information so we can really assign certain areas to given polymers. So we could also follow this nicely with adhesion or elastic modulus. You see that the size of the feature decreases once we reach more or less 50-50 combinations. There's much more to show, but I don't have time because, of course, you can vary both the contribution of the number of chains and the length. So this is, there's a lot to play. So here comes the microscopy and spectroscopy, actually. So we started with the polymer brushes with a relatively large contribution of this polythiophene-based chains, let's call them, like this. And you can see from the topography that there are some sort of I don't know, flower-like structures that with the optical phase, with the absorption mapping, we realized that they can be assigned to the to the carbonyl bond that is typical for this monomer. So these are the spectra. So we could assign those areas to these polythiophene-based brushes. But basically, if you realize that these are the spots we captured, you can see that, of course, there is majority of these polythiophene brushes in those areas. So they are not empty, of course, they are full of polythiophene-based brushes. But they are also thiophenes here. So this is not a large-scale phase separation. This is just that majority of polythiophene are here, and here some PSS and some hidden polythiophene-based brushes underneath. Because fortunately, you can see that we get a very nice bands here, characteristic of this PSS, so we could perfectly, assign the features on the surface. And and of course, if you go a little bit off the peak resonance, so to 1800s, you see no contrast. So this is a clear indication we really deal with carbonyl bonds here coming from these polythiophene-based brushes. So we played a bit with surface treatment, with solvent treatment, I would say. So dry systems, and we also changed actually the contribution of the brushes. So you see that the features, the previous one disappeared, and we have more or less, let's say, uniform distribution of much smaller domains. Yeah, but they can still be assigned to these polythiophene in the dry state, but on the same. And if we treat it with water, it appears that the PSS brushes sort of protect the hydrophobic polythiophene-based chains from the contact with water and cover them, and that leads to, let's say, reduction of the contrast, disappearance of the bands, of the domains that we see. Okay, I'm approaching the end. Okay, more or less, I can skip this just to show you that the very recent result, that if we actually, the previous results I showed for the brushes that were actually not conjugated. So there were thiophenes, free thiophenes. If you treat it properly and conjugate, the conformations are fixed and they are no more mobile. So there's no, whatever you treated with water, toluene, whatever, it is fixed. And you see the domains disappear. And this is actually what we wanted. We wanted really a kind of molecular mixing and fixing this situation. So for various combinations, you see also the change of the adhesion, which is like a homogeneous. There's no differences in adhesion like I showed before. It's just the growing adhesion because of the growing contribution of the polythiophene-based brushes. And we also did profiling, SIMS profiling to realize that we really have here the situation before conjugation. We have a large surface dynamics that disappears after conjugation, and we see just it goes down to the surface, and the contribution is just equal. No maxima, no minima here. The final slide. So at the end, I started with saying that the sample appeared to be really interesting. And that's what we really achieved, is that if we compare the classical P.PSS films and you compare the conductivity, vertical and horizontal, you see this is 0.14. So the horizontal is actually almost 10 times larger than the vertical. While in our case, you see almost 180 larger vertical than horizontal conductivity. And something still puzzling a bit is that we measured also the work functions. And the work functions for the pristine PMTM, so polythiophene-based, reached the value that is a world record for the conjugated polymers, which is 2.3 electronvolts, and for the mixed brushes 2.9, which is on the level of metallic calcium. So, and they are still stable in air. Yeah, at the end, I would like to thank, I should start probably from Adrian, who really contributed enormously with this essence NOM measurements, but also the other collaborators from my group, from the group of Professor Bernasik in the AGH University of Science and Technology. These are the persons who contributed the most in the synthesis. And thank you for your attention. Thank you.